Welcome to Q-CTRL's webinar on improving quantum hardware with quantum control. Hello, everybody. I'm Michael Hush, and here today with me, I've got some other members from the Q-CTRL team who'll be presenting some of the talks they did at the APS March Meeting. First up, we have Andre Carvalho, who'll introduce himself.
Hi, I'm Andre. I'm the head for quantum control solutions here at Q-CTRL. Then we have Chris.
Hi, I'm Chris. I'm a senior quantum control engineer and part of the quantum professional services team.
And finally, Lee.
Hi, I'm Lee. I'm also a senior quantum control engineer at Q-CTRL, part of the quantum product team.
Great. So today our session is going to go for around an hour. Let me just get to the next slide. Great. So we'll have multiple opportunities to ask any questions you may have. If you want to ask a question, please use that Q&A button. Don't put it in the chat. If you hit the Q&A button, then we'll be able to get to it. And also, if you've got a question which we don't have time to get to in this session today, we'll follow up with an email afterwards, so you'll make sure you'll get an answer. After we've had the webinar, you'll get an email with a survey. We would really appreciate if you fill that survey out. It helps us better understand how to improve the webinars in the future. And of course, it also gives you a chance to get into a draw for a $50 Amazon gift card. So it's worth your time. And finally, at the end of that survey, there's also a link if you want a follow-up call. So if you want to have a chat with us about any of the products that are mentioned today or any of the research that we go through, we'd be more than happy to have a chat with you. So that's so the format of today is going to be in 3 parts. First, we're going to the first presentation is going to be presented by Andre, who's going to present some pulse optimization results that we have done through IBM's Q's online cloud hardware. Then the next talk will be by Christopher Bentley, who will go over the optimization of some parametric gates for a Rigetti system. And then finally, Lee will do some presentations on some noise reconstruction techniques, which have been demonstrated both in theory on NV centers and also at an experiment with cold ions at the University of Sydney. So let's get started with the first presentation by Andre.
Hi, my name is Andre Carvalho, and today I'll be presenting the results from the work that our team at Q-CTRL did on pulse optimization for error-robust control on cloud-based superconducting hardware. Starting from a simple model of the quantum system, we'll show how our optimizer can be used to design robust gates by shaping the microwave pulses that drive the superconducting qubits. We'll also demonstrate hardware performance improvement by running experiments using these customized pulses on IBM quantum devices. Let's start with the following scenario. Imagine that you have a quantum circuit representing an algorithm that you want to solve using a quantum computer. The circuit is composed of multiple gates that, at the hardware level, are implemented through a real physical interaction with a qubit. Let's take this single qubit rotation, for example. In the IBM quantum hardware, such a gate is performed by applying a microwave pulse on the desired qubit. In fact, an arbitrary qubit rotation can be performed by combining pion 2 X rotations interspaced with Z rotations, as shown in this diagram. In the real device, this operation is imperfect and will lead to errors in the execution of your algorithm. What we'll show here is how one can use Q-CTRL's tools to design gates that are less susceptible to noise and errors in the device. This diagram shows 2 possible strategies for gate replacement. We can start from scratch and optimize this parametrized U3 gate as a single unit, or retain the structure used on the IBM devices and optimize these X pion 2 gates, which are used as building blocks for arbitrary rotations. In any case, the idea is to obtain customized gates that outperform the out-of-the-box native gate. Let's consider this diagram representing the different stages of the gate implementation. You pick your gate, which is represented by a given pulse. Internally, this pulse is created by the arbitrary waveform generator, and will pass through control lines before finally reaching the qubit. But what we need to know about this whole chain to design a robust pulse? Well, ideally, everything. Of course, the more we know about the system, the more detailed our model will be, and the better our ability to control the system. However, in this case, we can do a pretty good job using a basic model for the system. For example, here we'll just assume that we know the form of the Hamiltonian that performs the gate, given by this HC term in this expression. To design better gates, we also need to know what we are fighting against. In this case, we are considering two possible sources of noise: fluctuations in the control Hamiltonian itself, as represented by this beta term, and a dephasing process proportional to the sigma z operator, and this slowly varying stochastic variable eta. The control Hamiltonian represents a single qubit drive written in terms of the Pauli operators and modulated by the pulse envelope gamma of t, more commonly written in terms of the I and Q components for superconducting devices. Note that the ability to shape this pulse envelope is exactly what's required from the optimizer to generate our robust gates. In the IBM quantum systems, Qiskit pulse provides the interface that allows one to implement pulses with arbitrary shapes in their devices. Now that we have the model for the control Hamiltonian as well as the noise that we want to suppress, we can give this information to the Boulder Opal optimizer to find the desired gate. The diagram on the left shows the steps of this process. We input the parameters of the system like maximum Rabi rates and hardware time resolution. We also input optimization parameters like your target gate, its duration, and the number of segments in your pulse. Then you create the Hamiltonian with the optimizable variables, in this case, I and Q. If you want to generate a robust pulse against a specific noise source, you add this term as well, and you are ready to run the optimization. The outcome of the optimization is a piecewise constant pulse, as the one shown on the right. This one, in particular, is a pi pulse created to be robust against dephasing. With this pulse at hand, we are now ready to implement it in the hardware. This diagram represents the experiments we run. Our customized gate is sent to one of the IBM devices, and the excited state population is measured for different points in time, showing the system dynamics up to the gate duration. The solid line corresponds to Q-control numerical simulations, while the circles are the experimental data. The experimental points clearly deviate from the expected numerical curve, indicating that something is not quite right with this implementation. Looking at the pulse shape, we see that it has abrupt changes in its values, and this can cause problems. This fast pulse variation can exceed bandwidth limitations of the hardware electronics, for example, leading to discrepancies between the designed and the generated pulse. Furthermore, the control lines have their own characteristic transfer functions, so that the pulse that reaches the qubit can be actually a distorted version of what's generated at the AWG. One great feature of our optimizer is that it has a built-in capability to introduce constraints based on hardware restriction and imperfections. In this case, we smoothen out the pulse by applying a filter that removes its higher frequency components. This is easily incorporated in the optimization flow on the left, with a cutoff frequency defined by the user. With this single extra parameter, we obtain the smooth pulse shown in the center figure, and the measured dynamics is now in good agreement with the numerical simulation. Now that we have pulses that are behaving as expected in the hardware, it's time to experimentally demonstrate their robustness. In this slide, we have the default IBM Pi pulse and 3 robust pulses designed to be robust to amplitude noise, dephasing, and to amplitude and dephasing simultaneously. To show robustness, we run the experiment as before and measure the excited state population at the end of the gate. In the left figure, we plot the gate infidelity as the detuning between the qubit and the local oscillator varies. The pulses that were designed to be robust against the phasing are insensitive to the tuning, as indicated by the flat response. For the default pulse, on the other hand, the infidelity quickly increases as one departs from the central point in the graph. On the right plot, we have a similar experiment where the error in the control pulse amplitude is varied along the horizontal axis. Again, the performance of the default gate quickly worsens as it moves away from the central zero error point. The amplitude robust pulse shows a flat response across the whole range investigated. Interestingly, the dephasing robust pulse, even though was not designed for this, also shows a certain degree of amplitude robustness. The performance of our gates was also analyzed using randomized benchmarking. On the left plot, we have the fidelity as a function of the Clifford length for RB procedures where the Clifford gates are made up of the default IBM gates, shown in black, or Q-control dephasing robust optimized gates, in purple. Our pulse can outperform the default ones by a margin around 10 to 20%, despite their longer duration. The most important difference, however, appears when we look at the distribution of the RB outcomes for different sequence lengths. The IBM default pulse shows skewed and broad distributions, a signal of coherent errors. On the other hand, for the robust pulse, these errors are suppressed, leading to narrow and symmetric distributions, indicating that the errors are dominated by incoherent T1 processes. The existence of these coherent errors, as indicated by our RB results, can be further explored by performing experiments where the gate is repeated multiple times. As the gate is repeated, coherent errors accumulate, and we can see their effect clearly. The data in this plot shows the results of such an experiment for the IBM default and 3 different robust pulses. They perform similarly for a single application of the gate, but the default gate quickly loses fidelity as the number of repetitions increase. The curves in the plot indicate a fit using this function, which allows us to extract the errors coming from over or under rotation, this epsilon r term, as well as exponential decay given by the beta term. We repeated this fitting procedure for all 5 qubits in this particular chip and obtained epsilon r and beta across the device. Once these errors are found, we can estimate an overall error per gate, as illustrated in the plot on the right. We see a large variation across the device when the default pulse is used, but the robust pulses homogenize the errors, meaning that all qubits perform similarly. To test the stability of these gates over time, we repeat these experiments over multiple days, and the results are summarized in this 2D color plot. In the color scale, dark colors correspond to small errors, while bright yellow corresponds to the highest error. In the horizontal axis, we have the different qubits in the IBM Valencia backend, while the vertical axis corresponds to the different days the experiments were run. The numbers in the plots show the ratio between the errors obtained using the default gates and the errors obtained using our robust gates for the corresponding qubits and days. The changes from bright to dark colors along horizontal lines in the plot for the IBM default pulse show the large variability in performance across different qubits in the device. Note also that despite the daily calibration of the default pulse, there is also a large variation from day to day for the different qubits in the back end. This is in strong contrast with the Q-control results that show a much more uniform error per gate across device and also over time. The stability over time is particularly striking given that our pulses were calibrated on August the 3rd and used throughout the week without further calibration. This is a substantial gain in machine time, as daily gate calibrations can be skipped for these pulses. The results shown in this slide correspond to the same experiment as in the previous one, but now with the gates applied simultaneously on all 5 qubits in the chip. Running gates in parallel whenever possible is obviously advantageous as it reduces the execution time. However, driving the qubits at the same time can lead to poor gate performance due to crosstalk between the qubits. This is clear for the IBM default pulse, where the errors increase substantially as compared to the case of the gates applied separately. For our robust pulses, however, the performance remains basically unchanged for the dephasing and amplitude robust pulses. The robust pulses provided a 10-fold improvement in hardware stability over time and across the device, as well as a 10 times improvement in single qubit gate performance. In summary, in this talk I showed you how to design robust single qubit gates based on a simple model for the hardware, and also demonstrated the performance improvement of these pulses in a real cloud-based quantum device. In my last slide, I want to address a question that some of you may be asking right now. What if I don't have a good model for the quantum system? This is a question that we at Q-Control have been exploring as well, and I'd like to point you to 2 talks from our team. In their presentations, Yuval and Mirko will show how one can treat the quantum hardware as a black box and use machine learning techniques to design single and 2 qubit gates that outperform the default gates on IBM quantum devices. Thank you for watching this presentation from Q-Control. If you have any questions, you can reach out to the team by going to qcontrol.com.
Hello and welcome back, everybody. We've had a few more people join during that session. I forgot to actually do the poll at the beginning because it's a bit early here in Australia. Actually, Andre got up at 4 a.m. He's up in Brisbane, on the Gold Coast. So let me just start that poll. So just to learn a little bit more about who's here. So if you wouldn't mind filling in those answers while we continue with the next section. So at the end of each presentation, there'll be a chance to ask some questions, and we've already got some coming up now for Andre. Let's have a look. Sorry, I'll just get my question panel. So our first question is, how is the fidelity affected by the infinite slew rate of the pulse shape?
All right, so in the same way that I had in that plot showing when the pulse is varying quite rapidly, that the dynamics is affected, also does the final fidelity. So depending on the actual characteristics of the electronics, right? So if the pulse is varying too rapidly, then the fidelity indeed decays. Yeah.
Yeah, that makes sense. Next question is, how does the optimizer include robustness?
Right. So when we look at the cost that we have for the optimizer, one part of the cost is the fidelity, is the gate fidelity, right? And the other part of the cost is related to the sensitivity of that gate to noise. So we do that through what we call filter function that we can calculate using our product Boulder Opal, and that's going to include. So basically, we add to the cost function the response of the system to noise at low frequencies, and so the robustness is included in this way.
Great. Finally, another good question: how does the fidelity depend on the input states?
Right. So no, the fidelity is calculated based on the actual operation. So basically on the gates that you want to achieve. Yeah. So it's not the state fidelity, but it's the fidelity of the operation.
Yeah, exactly. And I guess that's the important thing also with the addition with the randomized benchmarking results. Maybe one last question before we move into the next section. How easy is it to go from the pulse design to the implementation on the IBM device?
Right. So in terms of integration and easy to use, it's pretty simple. So in that flow that I showed, we have the design of the pulse, and then in the end, what we have as an output is just a list with the pulse envelope. So it's a list of complex numbers indicating the amplitude and phase of that pulse, or I and Q, if we are thinking about the quantities that we use on superconducting qubits. So once we have that, then for IBM, we use Qiskit Pulse, where we can just plug those values and let the IBM implement that pulse. Of course, from the design, as I mentioned, from the design to the implementation, so that part is really an easy integration, but we also have the calibration that we do ourselves, and we can do that manually or using our automated optimizations as well.
Yeah. Well, there is one final question actually, which might be better answered by Chris with his upcoming talk. So can you do more complicated gates as well? And Chris, the answer is?
Yes, we can. Hopefully the next talk will help with that. Also, the next webinar will have more information there too.
Yeah. Oh, I forgot to mention that as well. At the end of those talks, those presentations by Yuval and Mirko, they'll be at the next webinar next week. So I'll just end that poll, present the results. Yeah, so it's good to see a lot of people coming here who missed the APS March meeting. So yeah, some of these talks will be new to you guys. Hopefully you can learn some new things. And just highlighting, it looks like most of you have access to cloud quantum computing hardware. So in both of the presentations that we'll be talking about, in order to get the most advantage from your cloud quantum computer hardware, you'll need to use some type of lower level access like OpenPulse, or Chris, what's the name of Rigetti's access?
Quilty on Rigetti.
Yeah, so we're seeing a move by most companies also to provide this lower level access as well. And if you have more questions around that, please come and set up a session with us afterwards. We'll be happy to talk about it with you more. So I'll just start the next presentation.
Hello, I'm Christopher Bentley, a senior quantum control engineer at Q-CTRL, and I'll be presenting our work on fast, noise-robust pulses for parametric entangling gates in superconducting qubits. Our colleagues at Rigetti also contributed to this collaborative work and presentation. Quantum computing offers a fundamentally different computing paradigm than classical computing. This quantum paradigm offers exponentially better resource scaling for solving important problems, known speedups in others, and great potential for still broader application. Superconducting qubits in particular are a world-leading platform for quantum computing, and access to these systems has moved out of labs and throughout the world through cloud access to systems like that in the schematic shown from Rigetti. Nonetheless, challenges still remain in this era of noisy intermediate-scale quantum devices, as noise sources still impact the quality of computing operations, or quantum logic gates, and thereby limit the capabilities of algorithms on real hardware. In this presentation, we apply Q-CTRL's expertise in quantum control engineering by optimizing and modulating control pulses to improve the robustness of parametric entangling gates. These gates are employed as entangling operations, a computational building block on Rigetti superconducting qubits. So what are parametric entangling gates? These are a form of 2-qubit quantum logic gates that can be used to provide an entangling operation in quantum circuits for computation. Consider 2 superconducting transmon qubits, one with a fixed frequency denoted by F, and one with a tunable frequency denoted by T. Both qubits have transition frequencies, which are depicted by solid lines on the slide. The 0 and 1 levels can be used as logical qubits, and the 0-1 transitions are marked. The 1-2 transitions for each qubit are also shown, where 2 is an auxiliary energy level, and the 1-2 transition has lower frequency than the 0-1 transition due to the anharmonicity of each qubit. To generate interaction between these qubits, flux modulation is applied to the tunable frequency qubit, which modulates the transition frequencies in time. So we have shown the average transition frequencies denoted by the bar over the F. The average frequency is then dressed by sidebands, shown as red dashed lines, which are spaced by the modulation frequency. When the modulation frequency is carefully chosen, this produces an effective resonance interaction between the 2 qubits. Then current exchange occurs such that population can move between the 2 qubits. For a particular choice of the modulation frequency, coherent exchange occurs between the 1-1 and 0-2 states, and here the effective resonance is marked by the gray line. By tuning the length of the flux pulse, population can be transferred out of the 1-1 state to 0-2 and back again, inducing a pi phase and performing a CZ gate. To compute with these gates in practice, we need to be aware of the noise processes that impact their performance. Flux noise can significantly reduce the fidelity of parametric gates. However, AC or dynamical sweet spots have been derived and demonstrated, which render the gates first-order insensitive to 1-on-F flux noise. In the top plot, the average transmon qubit frequency shift induced by modulation is shown, and the turning point can be observed where the flux modulation amplitude is at 0.6 on the x-axis. The frequency shift is first-order insensitive to flux amplitude changes at the turning point, giving rise to the gate insensitivity. The dephasing timescale is shown in the lower panel over the flux modulation amplitude. At this 0.6 amplitude dynamical sweet spot, the dephasing timescale is around as high as when no flux modulation is applied. The paper shown by the Rigetti team demonstrated high fidelity gates by making use of this dynamical sweet spot. In this presentation, we will be looking at moving from a sweet spot to a broader, robust regime for parametric gates. Note also that replacing a single frequency flux drive with bichromatic modulation can be used to engineer properties of the sweet spot. And you can check out the talks and the paper by our colleagues at Rigetti for more information. The dynamical sweet spots that we've been discussing arise at turning points of the tunable qubit's average frequency, as for instance shown by the white dashed line in the left plot. The resonance conditions for the flux modulation frequency also depend on the tunable qubit's average frequency, which is shown in the color scale of the left plot. Here, the flux frequency and amplitudes corresponding to CZ gate resonance conditions are marked in red and blue dashed lines for two different transitions. The dynamical sweet spots are at the turning points of the resonance condition curves. This can also be observed in experiment. The right-hand figure shows half a CZ gate where population has been transferred out of the 1-1 state when the resonance conditions are met. For flux noise robustness, we look at the turning point or the curve of the boomerang to find the sweet spot. Typical parametric gates involve pulses with fixed frequency, amplitude, and phase, as shown here in blue. Scanning the amplitude and frequency in experiment for half of this pulse lets us see the effective population transfer regions out of the 1-1 state that we require for a CZ gate. There is a very small region depicted with a pink point corresponding to the robust sweet spot. A key question here is, can robust solutions exist outside this tiny parameter region? At this point, we introduce modulation of the applied flux pulse, which can be optimized to improve robustness. On the top left, you can see an optimized flux pulse envelope where the phase is modulated over time within constrained limits for pulse smoothness. We introduce here a robustness infidelity measure to assess the robustness of the optimized gate. The infidelity of the optimized pulse is added to the infidelities obtained by increasing and decreasing the pulse amplitude by 4%. Using this robust infidelity measure as a target amounts to a simple grid-based optimization for flux amplitude robustness. The figure in the bottom left demonstrates, first, that a broader range of gate durations can be performed with amplitude robustness by using phase modulation, and second, that the breadth of the robust region is increased slightly for the optimal duration. The robustness infidelity is slightly improved for the best gate duration. On the right-hand side, varying the frequency and amplitude of phase modulated pulses can be observed in experiment to transform the shape and location of the sweet spot on the boomerang curve. Amplitude modulation can be used with similar effect to phase modulation. But can we have still more control over the robustness region? Let's now add in single qubit drives for the 2 qubits, where the I and Q components for an example drive with a fixed maximum Rabi rate are shown on the left. And for simplicity, both drives are at the transition frequency of the fixed frequency qubit. Applying these drives in combination with a flux pulse greatly increases the breadth of the robustness region for different pulse durations, seen by the lower infidelity measure at each point. And it also allows a much broader range of gate durations, and thus faster gates. These gates still retain flux amplitude robustness. When we have the additional control knobs provided by the single qubit drives, we can also introduce robustness to different noise sources. Here we show that adding the single qubit drives greatly increases robustness to ambient dephasing noise. This can be seen in the left-hand figure, where the flat, low infidelity region shows the robustness provided by these controls over a quasi-static scan of detuning for both qubits. Filtering the controls to produce smoother drives, as shown on the right-hand side, reduces the available control and thus reduces the robustness to dephasing noise, depending on how much filtering is required. Here, very high-powered drives with maximum Rabi rate of 100 megahertz are applied, but the same effect can be shown for lower powers. Through this presentation, we have seen that robustness is critical for high-fidelity parametric entangling gates. We can enhance robustness to flux noise, which is provided by dynamical sweet spots through modulation of the flux control. We can further enhance this robustness by adding single qubit drives, which can additionally be optimized to provide robustness to other noise sources, such as ambient dephasing noise. Furthermore, the combined flux and single qubit drives enable faster gates than those performed just with flux control. The next stage of this work is to apply these optimized flux and single qubit controls in experiment, and to quantify their performance and robustness on the chip. We're very excited to see where that will take us. Thank you for watching this presentation from Q-CTRL and Rigetti. If you have any questions, you can reach out to us by going to qcontrol.com or rigetti.com.
Welcome back again. Great. So we've already got some questions coming up. First one is, what kind of optimization techniques are used for the pulse design? Maybe Chris, you can address that.
Sure. So one of the components of the optimization that I can talk about here, I think freely, is that the optimizer is quite flexible. And so when you are describing your system in terms of the Hamiltonian and the flow from your control variables through to your target measure, which might be your infidelity or some other cost, including robustness, it can keep track of nonlinearities in that map, and it performs very well in the way that it keeps track of that flow of data.
I can maybe jump in. But yeah, that's basically what Chris is saying is right. We can say a little bit more in that the key difference, I guess, Chris is highlighting is it goes well beyond GRAPE. GRAPE makes a lot of very strong assumptions around how the pulses are structured. And as Chris is highlighting, what we do is we have a special way of approaching design where you just give a graph. So it can have a nonlinear relationship, it can have bandwidth limits, it can be synthesized of a variety of different pulse shapes. And so what that allows you to do is, because it's derived as a graph, just behind the scenes a bit, we actually use TensorFlow that allows us to analytically take the gradient and really accelerate the optimization. So we do highly efficient optimizations. We have cloud resources to accelerate them as well. So on our top plan, I think we get over a factor of 100 improvement for large systems compared to running it locally on your computer. And what was the other thing I wanted to highlight? The other nice thing about it is that it's very flexible, so you can do anything from GRAPE to crab-like optimizations or anything in between. So it really is whatever optimization you're trying to do, it can be used to achieve that goal. Next we have, how does your optimization deal with errors during readout?
So there are different ways to tackle this. In a lot of the results that I presented, they're still theoretical because the implementation work is still underway at the moment with Rigetti. So watch this space for more experimental results. But one approach to dealing with readout errors is, for instance, to do gate repetition, where if you use higher orders of the gate where you know what the outcome is expected to be and where you still characterize the full space of inputs to outputs, so the full gate performance, then you can track back the performance of the individual gate components with a much smaller component of readout error.
And I think I wanted to highlight, so Andre also wrote a calibration notebook as well, which goes into that in detail. Isn't that right, Andre?
That's right. So when we do the calibration, we do a test. We do multiple repetitions of the gate so that we minimize the effect of that. Yeah.
So there's an application note on docs.com, which you can look at, and that's all implemented. Another question is, can you study more systematically the gate time and thus identify what the quantum speed limit is in the presence of noise? I haven't done this, but I'm going to let you go first.
Sure. So yes, this would be interesting to do. There are always interactions which I guess you're working with particular resonance transitions in the parametric gate. And so the interaction which is caused by the flux drive is always going to be a determining factor in the duration of the gate. When you add in the single qubit drives, these can complement that flux drive and probably improve, or we saw that the robust region certainly improves as you add these single qubit drives. Practically in experiment, there are also limitations like the power of those single qubit drives, which will limit how much you can complement and help the gate time. So I suspect this will depend on the specific implementation to some extent in that way. Michael, did you want to add something?
Yeah, so I guess the other thing I was going to mention is we actually have a feature potentially coming up where you'll be able to add a cost associated with the total time that the pulse takes. And so then you can begin to do trade-offs on how long it takes versus how much of a high fidelity you want, which heads towards investigating time optimality. I think, Andre, did you also look at time? I think you've used the package to investigate the speed limit for Morgan-Sorensen gates, isn't that right?
Yeah, we did some investigation on that direction by actually including the duration of the gate as one of the things that we want to change. And but we haven't really gone too far into the idea of speed limit.
Yeah. So but I would just say basically our investigations, you can use the tool to do this and just move the horizon down, and you move the duration down and just see what happens to the fidelity. So you're more than welcome to investigate it. And yeah, as I said before, there's a feature coming up. So if you'd like to book in a time with us after this to chat about it, that'd be great. And maybe one more question before we move on. For Chris, why have you chosen that particular robustness measure?
Sure. So this partly comes from an understanding of the landscapes when you scan the amplitude and the frequency and you look at the infidelity over that landscape. What you could see in those plots was what I call a boomerang curve. You've got this resonant area which sweeps over a curve where the desired transition is happening. But if you move away on the y-axis or the amplitude axis, you've got what usually looks like a quadratic shape. And so if you weight your infidelity based on the center of that quadratic curve, which is where your target gate operation is happening, and the lowest infidelity, and then you also include grid points from a little away from that minimum, then what you're doing is you're sampling the curve of that Gaussian shape, quadratic shape. And that gives you an indication of how quickly the infidelity grows as you move away from your ideal amplitude.
So let's move on to the next presentation by Lee. And again, if you have further questions, we'll answer them at the last section.
Hi, my name is Lee. I'm a quantum control engineer here at Q-CTRL, and in this presentation, I'll be talking about how to reconstruct the noise power spectral density in quantum device using convex optimization. The performance of current state-of-the-art quantum device, including quantum computers and sensors, is limited by noise. Any quantum device has some inevitable coupling to its outside environment, which introduces stochastic noise processes. Quantum control techniques can compensate and correct these noises, but they have to first be characterized. A noise spectral density that provides information about the noise strength as a function of frequency is a useful characterization tool. Often the origin of a noise can be recognized through spectrum features or the power law a noise power spectrum has. Furthermore, the noise power spectrum can be used to engineer controls that are robust to the noise in the relevant frequency windows. Characterizing a noise spectrum can be practically difficult. with quantum devices because standard characterization techniques typically only work at room temperatures. When a device is brought to cryogenical operating temperatures, the preview characterization might become inaccurate. Here we present a novel approach where we characterize the noise using the quantum system itself, for example, the qubit as in-situ detectors. Let's have a look at the overall process of characterizing the noise power spectra. So here the top left figure shows the dynamics of a qubit is affected by some noise process, which can be characterized by this power spectrum density function. We can apply different control signals directly to the qubit. For example, ideally, these control signals are equivalent to applying an identity gate for a noise-free qubit. We can then measure the final state of the qubit to assess the infidelity of the control operations. The relation between noise and control signals can be described by a so-called field function in the frequency domain. In fact, each control signal here corresponding to a field function as shown in the bottom left figure. On the top right, we show controls that are generated by modulating a Gaussian signal with sine function of different frequencies. By changing the frequency, we have a sequence of field functions that scan the frequency range we are interested in. Once you have the measurement and field functions, it becomes an inverse problem to identify the underlying noise spectra. And in this presentation, we will show a novel approach to solving this inverse problem using convex optimization. Before diving into the details, we briefly talk about the standard way of performing noise reconstruction. For example, to characterize the dephasing noise, it usually consists of 3 steps. First, to generate a set of CPMG pulses and measure the final state of the qubit after applying each sequence. And finally, we reconstruct the noise spectra using the standard Suter-Alvarez matrix inversion algorithm. There are several issues with the standard approach. First, the CPMG sequences put a restriction on the density of measurements, since the peaks of the harmonics must line up within the band of interest. And also the CPMG sequences have higher order harmonics, which can lead to higher frequency noise process, incorrectly contributing to the reconstruction. So this is a process known as spectral leakage and often makes the reconstruction results unreliable. The Q-control approach to performing noise characterization consists of 4 steps. So compared to the standard method, it allows one to use arbitrary control sequences that are best suited to the reconstruction. We then calculate the corresponding field functions and reconstruction the noise spectrum. A key challenge to characterizing a noise power spectrum is to solve the inverse problem. So here we present the Q-control solution to this problem based on convex optimization. So first note, we are using a classical random process for describing the decoherence of quantum systems. That is, the system Hamiltonian is divided into 2 parts. One is to describe the control that apply on the system as they're often unitary operations. The second part describes the noise. Here, Nk is a system operator, and K labels different noise channels. Beta K are the classical random variables. This noise process are assumed to be stationary and independent. If the noise is weak, then there's a linear relationship between the corresponding field functions and the noise spectra, which is defined as the Fourier transformation of the autocorrelation function of beta. Here, Ij is the operational infidelity for control J, as we mentioned earlier. You can find the details of the derivation in the NJP paper. The second step is to discretize the integral and turn it into matrix form. Here, assume we just performing the discretization uniformly across the frequency domain. We will have a matrix F and a vector S. So each element Fk here is also a matrix, describing the filter function for the noise channel K, and each row corresponds to individual control. Similarly, Sk is a vector representing the noise spectrum of channel K that is to be reconstructed. So here matrix F is often a rectangular matrix, meaning we can't directly solve the equation by inversing F. And instead, we can reformulate the problem into an optimization problem. The objective function is defined as the distance between Fs and I plus a regularization term. We also introduce a constraint that the elements of S mustn't be non-negative since they represent the power. By minimizing the constraint objective function, the optimal solution should represent our best understanding of the spectrum. The regularization term can introduce certain prior knowledge about the noise. For example, you may choose to minimize the difference between adjacent elements in the solution. This effectively imposes a restriction on the result since we would not expect it to have a higher resolution than the field function itself. We often choose this term as a convex function, and the optimization problem itself is then convex and can be solved efficiently by the Q-control optimizer. Lambda here is a hyperparameter, and it's a positive value that represents the weight of the regularization in the solution. It is very important to find a proper hyperparameter for preventing the overfitting in the solution, which is a common task in machine learning. We use the cross-validation method to find a suitable hyperparameter, and this approach converges to an accurate reconstruction with sufficient samples. As an example, we consider a simulation of probing a magnetic field by measuring diffraction signals on the MV center. The control signal used here is called a stepping pulses, which is well known for being mathematically optimal in terms of spectrum concentration within a target sending band. And they have a tunable frequency response and therefore solve the spectrum leakage issue. Here, each pulse is designed to perform an identity operation if there's no noise in the system. And we only care about the defacing process related to the T2 time rather than T1, meaning the gate operation and measurement are short compared to T1. The goal is to reconstruct the noise spectrum at a low frequency range as highlighted. We will compare the result between standard approach and the Q-control approach. We first show the field function corresponding to each of the controls. In this plot, we can see the original noise spectrum, and a set of field function which look like colored peaks. So each colored peak corresponding to the field function of an individual control pulse. We can see that each control has a single narrow peak around the center frequency that is shifted for different pulses, and this peak sample the frequency range we care about. As a comparison, we also show the field function calculated with CPMG pulses. We can see that these high order harmonics outside the frequency range are very interesting, and this spectrum leakage can distort the reconstruction result. So here we compare the reconstruction result from the Q-control and the standard approach. The top figure is the result from the Q-control approach, and it shows an accurate high resolution result. The standard approach result is shown in red at the bottom. As we can see, the magnitude of some peaks are incorrectly predicted. The resolution is worse, and there are fictitious peaks arising, which could be due to spectrum leakage from the higher order harmonics in the CPMG field functions. It is clear that the Q-control noise reconstruction approach gives us higher resolution and also more accurate results that are robust to superior's higher frequency contributions. The noise reconstruction method has also been applied experimentally in the quantum control laboratory at the University of Sydney in collaboration with Q-control. Details of this demonstration can be found in the paper available on arXiv. A key innovation in this demonstration was using the spin motional entanglement to probe noise on the bosonic oscillator modes of the ion. In the figure on the right, we can see two reconstructions of the spectrum. The reconstruction in black was completed with sequences suffering the same spectrum leakage problems as the standard approach mentioned above. while the reconstruction in red was completed with narrowband Slapian pulses. We can see the black spectrum has fictitious peaks due to the higher order noise process interfering with the reconstruction process, while these are suppressed by use of Slapian controls. So this is a totally different physical setting from a single qubit subject to dephasing. But we can still use the identical technique due to the d-dimensional field function and flexible reconstruction algorithm we developed. In summary, we have shown a new approach to reconstructing the noise spectrum. As demonstrated in both simulation and experiments, we use narrowband Slapian pulses to optimally estimate the noise spectrum properties without leakage from higher frequency noise. And we use the convex optimization approach to reconstruct the noise spectrum density with a high resolution. Further work will look at automating the hyperparameter tuning process for our method and applying the algorithm to reconstruction problems with multiple noise channels. Thank you for watching this presentation from Q-Control. If you have any question, you can reach out to the team by going to qcontrol.com.
Hello and welcome back to the last section. So we've already got a question for Lee. Can I do this on multi-qubit systems?
Yes. So as long as you can apply direct control to the system and the span error is not the dominating error source in the system, then you can use our technique to do the reconstruction.
Another good question is, so what noises can you use this for? So what type of noises in the system?
Any type of noise, as long as it's weak, relatively weak in the system, and you can use this technique to do the reconstruction. So in the user guide on the Q-Control documentation website, we also demonstrate the amplitude noise, how to reconstruct the amplitude noise using our method.
Yeah, I think, and that's great advice. I think the only other part is sometimes when it comes to picking, if you have a more exotic type of noise, picking pulses that have the right sort of sensitivity so that they have these tight, the Slapian pulses that were picked have this narrow band feature. So designing pulses which have narrow band features for arbitrary pulses, arbitrary noises, there's a bit of an art to it. But if you have a particularly different type of system, please come have a chat with us, and we're happy to help out and figure out what is the best one for you. So we've got another question asking, so does this work for Markovian and non-Markovian types of noise?
Yeah, so the assumption we made in our model is the noise process is described by a classical random variable. So that could be Markovian or non-Markovian. So the essential thing is the noise must be weak, such that the linear relation holds. Yeah.
And that's what we've actually, when it comes to experiments, we tend to see that sort of quasi-classical treatment is quite good. So in the superconducting devices, stray magnetic or electric fields or slight mismatches in the component values tend to produce noises that look effectively classical. There is, of course, other techniques like system identification. If you have more coherent style noise processes, and there are features in Boulder Opal to deal with those kind of issues as well. One more question, could Tikhonov, I'm not going to say that word right, but basically, could Tikhonov regularization be a useful approach to solve your inverse problem?
Yeah, that's an excellent question. That's exactly what we one of the regularization we use to solve this problem. Actually, you can design any type of regularization term that's specific to your problem, because users often have better knowledge about the system. For example, if you want to find the noise peak for a really wide range of frequency domain, you may want to apply the L1 regularization, which you basically assume that your noise is sparse across that domain. And then you can use, say, the L2 regularization term, and to narrow down the reconstruction into a small range. to do the reconstruction.
And just so you know, we also have good defaults as well. So even if you don't have a lot of knowledge, the default settings are normally quite a good start. So Daniel asked, I don't quite get the point of how you're using the qubit in an in situ way compared to the previous work.
I think the main advantage of our method is we are not constrained to a specific type of control pulse. For example, the CPMG. We can use an arbitrary control pulse that's best suited to the system. For example, in the NV center example, we are using the sloping pulses, which you can deal with the spectral leakage issues. Yeah, that's the one of the reason why this method is good. And Michael, do you have anything to add?
Yeah, and so I guess around that's the point, is that so I guess a good analogy might be superconducting qubits. So if you're trying to measure the attenuation or noise processes on your control lines, it's true you can kind of run some processes at higher temperatures and check what the noise processes are in your device. But then when you bring your system down to cryogenic temperatures, or when you actually place it in a real kind of situation, it can change quite radically what the noise processes are, and then suddenly you can't use traditional techniques. So when we say in situ, we mean you're actually, as Lee said, we're applying pulses to the qubits themselves when they're operating in an environment like they would for the quantum computation or as a sensor. So, and what you do is you apply each pulse to the qubit and then do a measurement directly on the qubit. So you get a realistic model, an accurate model of the noise environment of that qubit when it is actually functioning as the device is expected to. So I think that's probably we're getting close to the hour now. So we'll probably end it there. Thank you very much for attending. Again, afterwards, you're going to get a link to a survey. It'd be great if you could fill it out, and you'll be able to go into a draw for a $50 gift voucher, so well worth your time. And if you would like to talk to any of us afterwards, please hit that link at the end of that survey, and you can book a time with us at whenever works for you. There'll be another webinar next week, which will have the other half of the talks from the APS meetings. So it would be great to see you there as well. Thank you very much, everyone.
Yeah.
See you.
Bye.